Hi, in this video we'll continue the problem solving session for quadratic equations. This is part 2 of the video. The first 18 questions were shared in part 1, so you should look at that. And in this video we'll look at some more problems which should help you apply these principles and learn these techniques which might be useful for you in exams. So let's start with this particular problem. Let ABC be real numbers with a greater than 0 such that the quadratic t of x is equal to ax square plus bcx plus bq plus cq minus 4abc has non-real zeros. This quadratic basically has non-real roots. Then we have to prove that exactly one of the polynomials t1x is equal to ax square plus bx plus c and t2x is equal to ax square plus cx plus b has only positive values. Basically, given that t of x has non-real roots, we have to prove that t1x and t2x have only positive value, just one of them. So since t of x has non-real roots, we can say that the discriminant of this t of x must be less than 0. Right? So discriminant is less than 0. And that condition can be written as b square c square minus 4a b cube plus c cube minus 4abc. That must be less than 0. Right? Now, what we need to do is we need to try to factorize this and get it to look like delta 1, which is discriminant of this, which is b square minus 4ac. Delta 2 is c square minus 4ab. Right? So we have to think of how we can factorize this one. Right? Now, if you just look at these two discriminants for the other two quadratics, if I multiply delta 1 times delta 2, let's see what comes. It is b square c square minus 4ab cube minus 4ac cube plus 16a square bc. Right? And notice that here you have b square c square minus 4ab cube minus 4ac cube plus 16a square bc, which is less than 0. So this is clearly the product of del 1 into del 2, which is less than 0, which means that one of the polynomials has to have positive values because either del 1 or del 2 is less than 0. Both cannot be negative, both cannot be positive, one of them has to be negative, which means that one of the equations has positive values. Since a is positive, this is an upward facing parabola. If del is less than 0, the parabola does not intersect the x-axis. Basically, that's why the proof is done. Okay, let's look at the next problem. Let p of x be a monic polynomial, with real coefficients of degree n of degree n which has n real roots. So p of x is a monic polynomial with real coefficients and degree n and has n real roots. Prove that if a, b, c are real numbers with a greater than 0 and p of c is less than equal to b square by a to the power n, then p of ax square plus 2bx plus c has at least one real root. Okay, so p of x is a nth degree monic polynomial with n real roots. And if ABC are real numbers with a positive such that p of c is less than this, and we have to show that p of ax square plus 2x plus 2bx plus c has at least one real root. So think about it, if p of x is degree n and has n real roots, let's call the real roots as alpha 1, alpha 2 till alpha n. That implies p of x can be written as x minus alpha 1, x minus alpha 2 till x minus alpha n. Because it is a monic polynomial, the coefficient at the top is 1. Right? Therefore, now p of c, if you think about it, is equal to c minus alpha 1, c minus alpha 2 till c minus alpha n. And it has been given that that is less than equal to b square by a to the power n. Right? Okay, so p of c is equal to this. What is p of ax square plus 2bx plus c? P of ax square plus 2bx plus c would be ax square plus 2bx plus c minus alpha 1. And similarly, ax square plus 2bx plus c minus alpha 2. And so on till ax square plus 2bx plus c minus alpha n. That is the value of this expression. Now, what we have to show is that p of ax square plus 2bx plus c has at least one real root. We have to prove that. So in order to prove that, we can do a contradiction proof where we assume that p ax square plus 2bx plus c has no real roots. This is our assumption which we have to prove is a contradiction. This assumption should lead to a contradiction. So that means if p of ax square plus bx plus c has no real roots, then what we need to have is basically all of the terms p of ax square plus bx plus c will be greater than 0. Right? Like we had written this as a product of factors ax square plus 2bx plus c minus alpha 1 times ax square plus 2bx plus c minus alpha 2 till ax square plus 2bx plus c minus alpha n. So if it has no real roots, then the value of this expression will be greater than 0 because a was positive, it's an upward facing parabola. So therefore, each of these is positive. Each of these expressions must be positive because the overall thing is greater than 0, right? Now each of these expressions is positive, which means the discriminant, these are all quadratics. These are all quadratic in X. So the discriminant here must be less than 0. And the discriminant here must be less than 0 for it to be always positive. And the discriminant here must be less than 0. So what is the discriminant? If you see, this will become 4b squared minus 4ac minus alpha 1 is less than 0, which means b square minus ac minus alpha 1 is less than 0, right? Which implies b square is less than a times c minus alpha 1. And similarly, you get b square is less than a times c minus alpha 2, and so on till b square is less than a times c minus alpha n. For each of these factors, the discriminant has to be negative because all the factors are positive. Therefore, these conditions are coming and there are n factors, right? So if I multiply all of these n factors, I will get something like b square power n is less than a power n c minus alpha 1 c minus alpha 2 till c minus alpha n, right? So what I am getting is b square power n is less than a power n c minus alpha 1 c minus alpha 2 c minus alpha n. Basically, b square by a whole power n is less than c minus alpha 1 c minus alpha 2 till c minus alpha n, right? And we know that this expression is actually equal to p of c, right? So what we are getting now is p of c is greater than b squared by a power n. But in the problem it was stated that p of c is less than equal to b squared by a power n, which is a clear contradiction. This contradiction basically means that our initial assumption is incorrect. So p of ax squared plus 2bx plus c must have a real root. Because we said that it has no real roots, must have real roots. We have proved this by contradiction. That concludes the proof for this one. Right. Let's look at the next problem. Question 21. Find all pairs. Find all pairs a comma b of real numbers such that twice of a square plus 1 times b square plus 1 is equal to a plus 1 times b plus 1 times ab plus 1. This is the question. Now, we'll employ the usual technique where we'll convert this expression and we'll write it as a quadratic. You can choose to write it as a quadratic with variable a or variable b. Both will work. And this time we'll make it a quadratic in variable a. So after a little bit of algebraic simplification, which you can check for yourself, you will get that this can be written like this. Minus b plus 1 whole square a plus 2b square minus b plus 1 equals 0. So this is the quadratic in A, and because A is belonging to real, the discriminant of this quadratic is greater than or equal to 0. Right? So discriminant here is b plus 1 power 4 minus 4 times b square minus b plus 2 times 2b square minus b plus 1 is greater than or equal to 0. Now we just have to simplify this a little bit. Again, some algebra that I'm skipping. So you have to work it out yourself and you will realize that this is equal to minus of e minus 1 whole square to 7b squared minus 2b plus 7 is greater than or equal to 0. Now this part is always less than or equal to 0. So this has to be also negative. If you put the minus sign on the other side, you get b minus 1 whole square, 7b square minus 2b plus 7 is less than or equal to 0. So basically we need this part to be less than or equal to 0. Okay? Right. But if you think of 7b square minus 2b plus 7, the discriminant of this is 4 minus 4 into 49. Discriminant is less than 0, so this is always positive. It's always positive. So how can you get this is always positive and this is a perfect square? The only way this will be less than equal to 0. It cannot be less than 0. It must be equal to 0. Okay? Because this is positive and this is greater than equal to 0. Cannot be less than 0. Must be equal to 0 and therefore b must be equal to 1. And if b is equal to 1, we can easily find the value of a. Let's put b is equal to 1. You get 2a square minus b is 1, so minus 4a. And 2 minus 1 plus 1 plus 2 is equal to 0. We get a square minus 2a plus 1 is equal to 0, which implies a is also 1. So according to the conditions of the problem, we converted it into a quadratic in a. And for a to be real, the quadratic had to have a negative discriminant or positive discriminant. After simplifying it, you realize that it cannot be positive unless it is 0. That's the only possibility. That gives you the condition that b is 1, and from there we can find a is 1. So the only pair that satisfies this is 1, 1. That is the pair for a and b that satisfies this range. Okay. The next problem is this one. Prove that for all real numbers, prove that for all real numbers, a, b, c, 2a square plus b square plus 3c square plus d square plus 2e square is greater than equal to twice of ab minus bc minus cd minus d plus ea. Okay, so again, the question has 5 variables, but you can make it easier by thinking of it as a question involving just a quadratic in a. So I'll say like this, 2a square is the quadratic term. These are all constant terms. You get a minus 2ab and a minus 2ea, right? You can say minus 2a b plus e and you bring it to this side. And you have plus b square plus 3c square plus d square plus 2e square. Remaining terms are plus 2bc plus 2cd plus 2d is greater than equal to 0. Right. So this is coming right now. This is the quadratic in A, and the left hand side is a quadratic in variable A with a positive leading coefficient. Therefore, the only way this is greater than equal to 0, the quadratic opens upward. So you can have either this case or you can have this case, right? Only way this happens is del is less than 0 or del is equal to 0. So your discriminant here must be less than equal to 0 for this inequality to be true. Discriminant in terms of a becomes 4b plus e whole square minus 8 times b square plus 3c square plus d square plus 2e square plus 2bc plus 2cd plus 2de. That has to be less than equal to 0. Now, a little bit of simplification here, you will be able to say that it is this expression can now be written as quadratic expression in b. You will get b squared plus 2b 2c minus e and plus twice of 3c square plus d square plus 3 by 2 e square plus 2cd plus 2de is greater than equal to 0. So I have, what have I done here? I have simplified my discriminant, brought it in terms of a quadratic in B. I have written it as a quadratic in B. And now this quadratic also is greater than 0. So discriminant with respect to b is also less than equal to 0. So I will do the same process basically here for it was for quadratic in A. Now we are doing it for quadratic in B. And let's write on the next screen the discriminant that comes for B. That is equal to 4 times 2c minus e whole square minus 8 times 3c square plus d square plus 3 by 2 square plus 2cd plus 2d is less than equal to 0. Again, simplifying this, you can write this as a quadratic in C now. C square plus 2c plus d plus d square plus e square plus 2de is greater than equal to 0. And again, following the same process, you can, or actually here, you can easily see that this is c square plus 2c e plus d plus d plus e whole square is greater than 0. So this becomes c plus d plus e whole square, which is greater than equal to 0. So this last inequality is true always. So if this last inequality is true, we can reverse all our steps and we can prove that delta b is less than equal to 0. And if delta b is less than equal to 0, the quadratic in B was greater than 0, which was coming from, which was basically the discriminant in A, which was less than 0. So all of the reversible steps are true. Therefore, our claim is true. You could have also done this problem in a different way, looking at the initial expression. You can try and complete the squares in the initial expression, basically. So, right, you can try it out. I will not get into it right now because anyway, we have approached the problem in a systematic way and we have solved the problem. Point was to look at it as a quadratic in A, analyze its discriminant, then the discriminant we have to look at as a quadratic in B and analyze its discriminant. And we got a true condition at the end. Okay, let's look at the next problem. If A, B, and C are real numbers such that ax square plus bx plus c is greater than equal to 0 for all real x. For all real x. We have to prove that 4a cube minus b cube plus 4c cube is greater than equal to 0. Right. Now, the first case that we'll take is the case where a is equal to 0. If a is equal to 0, the condition becomes bx plus c is greater than equal to 0 for all real x. And therefore, this cannot be true for all real x unless the coefficient of b is 0. So b must be 0 and c must be greater than equal to 0. So if b is 0, obviously c must be greater than equal to 0. So then 4a cube minus b cube plus 4c cube is equal to 0 minus 0 plus 4c cube, which is greater than 0, since c is greater than 0. So the case where a is 0 is pretty trivial. Here both a and b become 0 and c must be greater than equal to 0. So now we will look at the second case where a is not equal to 0. Right? A is not equal to 0 and then the quadratic is always positive has been given. Right? The quadratic is always positive, so it implies that it must have negative discriminant and positive first coefficient. So the statement of the problem itself implies that now if a is not 0, it must be greater than 0 and the discriminant is less than 0. Right? Less than equal to 0. So we have A is less than 0, A is greater than 0, and the discriminant B square minus 4AC is less than equal to 0, right? So that implies that 4AC is greater than equal to B square, which implies AC is greater than equal to B square by 4, that is greater than equal to 0, right? So we have AC greater than equal to 0, and we already know that A is greater than 0. So that implies that C is also greater than equal to 0, right? So now let's look at separate cases. We have AC greater than equal to 0, A greater than 0, C greater than equal to 0, and we have already established that AC is greater than equal to B square by 4 is greater than 0. Now if B is less than equal to 0, then what is the value of 4A cube minus B cube plus 4C cube? This term is positive. This term is positive. And if C is less than equal to 0, negative B cube is also positive. So it is clearly greater than 0, right? And the second case is if B is greater than 0. If B is greater than 0, we have 4A cube plus 4C cube, which is equal to 4 times A cube plus C cube, which is clearly greater than equal to 4 into 2 times A power 3 by 2, C power 3 by 2. This step is coming by A and GM inequality since A and C are both positive. So this is equal to 8 times root over AC to the power 3, and that is greater than equal to 8 times root over AC is greater than equal to basically B by 2. So B by 2 whole cube, which is equal to B cube. So what we are getting is 4A cube plus 4C cube is greater than equal to B cube. Therefore, 4A cube minus B cube plus 4C cube is greater than equal to 0. So we have proved case 2 also. We took basically two cases where A is 0 and A is non-zero. For A is non-zero, the case that A is positive is only case that is allowed. Once you take A is positive, from AC greater than equal to 0, we also know that C is positive. And after that, we are taking two cases for B. Both the cases, we are able to prove that statement of the problem. Right? Now, I'll look at one last problem. This is a very interesting one because it combines knowledge of geometry with quadratic equations. This is a USAG AJMO 2018. So let's look at this question. Triangle ABC with angle ABC greater than equal to 90 degrees is inscribed in a circle of radius 2, and x is a real number. X is a real number satisfying the equation x power 4 plus ax cubed plus bx square plus cx plus 1 equals 0. Where obviously small a is BC, small b is the length of side CA, small c is equal to length of side A. We have to find all possible values of x. Basically, you have to solve this equation given the fact that A, B, and C are side lengths of a triangle ABC, which has angle B greater than equal to 90 degrees. The triangle is inscribed in a circle of radius 2. If you have a circle of radius 2, the triangle is somewhere inside. draw a better figure. Something like this, A, B, C, and the circle has radius of 2. Right? The triangle is inscribed inside the circle. We have to somehow solve this problem, solve the equation for x. Right? Let's think about the expression that we have here. X power 4 plus ax cube plus bx square plus cx plus 1 was 0. Now, if you want, you can write this expression in terms of perfect squares. So what I can do here is this is equal to x square plus a by 2x whole square, which is basically x power 4 plus a square by 4x square. So plus 2 into x square into a by 2x. So basically this accounts for the first two terms if you think about it. And one extra term is there, which is a square by 4x square. Right? Then we can write this as c by 2x, actually square by 4, right? We can write this as cx by 2 plus 1 whole square, which will give us a c square by 4x square, and it will give us the cx term. It will also give us the 1 term. Right? But what we have created so far are two extra terms, a square by 4x square and c square by 4x square. So I'll write it together like this. It is b minus a square by 4 minus c square by 4 times x square. So basically what I have done is I have worked on the left hand side and written it as the sum of two squares plus a third term, right, equals 0. Great. So let's rewrite it on the screen. We have x power 4 plus ax cube plus bx square plus cx plus 1 is the same as x square plus a by 2x whole square plus c by 2x plus 1 whole square plus p minus a square by 4 minus c square by 4 times x square. We have to solve the equation equal to 0. So case 1 that we can think of is if b is greater than a square by 4 plus c square by 4. If that is so, then the last term is also positive, and these terms are anyway positive. So the sum of three positive things cannot be 0. So LHS is coming out greater than 0. So there is no x such that that can be true. There is no real x such that that can be true because it is all positive. So it cannot be equal to 0. Right? So that is case 1. So now that means that case 1 doesn't work. So we say v is less than equal to a square by 4 plus c square by 4. Right? Now, since angle ABC is greater than or equal to 90 degree, angle ABC is greater than 90 degree, that is an obtuse triangle, and in an obtuse triangle, the biggest side is actually bigger than the sum of squares of the other two sides. This is an extension of Pythagoras theorem. Basically, if it's an obtuse triangle, b square will be greater than a square plus c square. And this is c and this is a. So we have this inequality because the problem itself said that the triangle was obtuse. Right? So what we can say is from here we can conclude that 4b is less than a square plus c square. And a square plus c square is less than b square. Right? Using the two things that we have gotten, this thing and this thing. We are getting this relation. So basically b square minus 4b is greater than or equal to 0, right? This relationship is true for positive values of b if b is greater than or equal to 4, right? So b must be greater than or equal to 4 for the situation to work. However, if you think about it, b is the length of the longest side of the triangle, but the triangle was inscribed in a circle, right? Triangle was inscribed in a circle of radius 2, so the longest side is actually the diameter of the circle. So therefore, diameter of the circle is 4, so b cannot be greater than 4. This is wrong, right? Because the diameter is the longest chord in a circle. Triangle's length of the side of a triangle has to be less than. So b is greater than 4 is not allowed, which means we get that b must be 4, right? Okay. Uh, Now we basically have the equality for b is equal to a square plus c square is equal to b square is equal to 16. And the equation now can be written as x square plus a by 2x whole square plus c by 2x plus 1 whole square. And the third term was b minus a square by 4 minus c square by 4. So we know already that b is equal to a square plus c square by 4. The third term vanishes, right? So we have this equation, the sum of squares will be 0 only if two separate terms, have roots in common. So both have to be 0 simultaneously. The roots of this are 0 and minus a by 2. The roots of this are minus 2 by c. This is the only root of this. So we cannot say 0 is equal to minus 2 by c. That doesn't make any sense. So therefore, we must say that minus a by 2 is equal to minus 2 by c, which means that ac is equal to 4, right? Okay. Now, we basically get two equations. We get a square plus c square is equal to 16, and we get ac is 4. We already know b is 4, right? So from these two pieces of information, we can find a and c. That can be done in a straightforward manner if AC is 4 and a square plus c square is equal to 16. What we can say is that a square plus c square is 16. So correct. So we can solve it very easily. We can write c as 4 by a. Say a square plus 16 by a square equal to 16. And solve this equation for a. And basically you'll get a can be either root 6 plus root 2 or root 6 minus root 2. You should check this calculation. This becomes a quadratic in a. And if a is that, c can be basically root 6 minus root. And the other option for c is root 6 plus root. So the pairs of a and c are known now. And now what we can say is that what are the solutions for x? X must be equal to basically minus of a by 2. Right? Minus of a by 2. Minus of root 6 minus root 2 by 2 or minus of 6 plus root 2 by 2. These are the two possible values of x that we get. Because we are using the first term in that sum. We had said x square plus a by 2x whole square plus c by 2x plus 1 whole square is 0. Both have to be 0 simultaneously, so x values are coming out to be these two. Right? Now, we know a particular value of x has to be either this or this. So, what you can do is you can verify whether these values satisfy the condition or not. You can say that you have a right triangle ABC inscribed in a circle of radius 2 and A is root 6 plus root 2, B is 4, C is root 6 minus root. This basically gives us the polynomial equation x power 4 plus root 6 plus root 2 x cubed plus 4x squared plus root 6 minus root 2x plus 1 is equal to. This is the polynomial that you get when you put the values of a and b, right? And basically, now you can solve this polynomial by factorizing it in the same way that we saw before. You can write this as root 6 minus root 2 by 2 x plus 1 whole square times 6 plus root 2 by 2 x whole square plus 1 equal to 0. So this is just to confirm that these values are going to work. It is actually going to turn out to be a 15, 75, 90-degree triangle. You should check this yourself as well. The key point in the problem was to look at the fourth degree thing and separate it out as three terms. Two of them are perfect square, one of them is the third term, which involves b minus a square by 4 minus c square by 4x square. Once you did that, you could say that basically we have b cannot be greater than 4 and b cannot be less than 4. B must be equal to 4 here. B cannot be greater than 4 because it is the side in a circle whose diameter is 4. So side length must be smaller than 4. Okay? Now you are basically saying that the third term vanishes and its sum of two squares is equal to 0, which will have a solution only if both of them are simultaneously 0. From where you get x is equal to either 0 or minus a by 2, and also it is minus 2 by c, from where we get ac is equal to 4. If AC is 4 and a square plus c square is 16, then the next step is basically finding the values of x, which is not at all hard. So that concludes the proof of this problem. The next chapter that we will start looking at is a chapter on inequalities. We'll do a couple of sections on inequalities because again, that is super important from the point of view of an Olympiad exam. Even from PRMO to RMO to INMO, inequalities are an important topic. So that is the next algebra topic that I will cover. And again, the way it will be discussed is through problem solving. We will go through a lot of theory while solving problems. So stay tuned for that video. Quadratic equations part of the algebra course is done. And if you like the content, please subscribe to the channel and share your feedback, comments, and what else do you want in different courses. I appreciate your support and please like and subscribe. That's all for this video. I'll see you next time.